Again, good morning. And today is March 1st. We are in the third week. We are still in Unit 2 for this class. We're still dealing with basically waves. Last time we did introduce the waves, basically the wave equation. And the lab, actually lab 2 is actually on Canvas too. So we're going to have lab session this afternoon. We can go through the lab, which is should be really a survey of wave phenomena. That's what this lab is. It has some components of other labs that we will have in the future, namely the parts of the optics, namely with the reflection and diffraction and all the behavior of waves. So it's mainly a survey of lab activities. Okay. So that's what this lab is, a survey of wave, basically of waves. And down the road, we will have some more in-depth discussion of some of these wave phenomena. Anyway, let me make sure that we're not disturbed. Anyway, so today we're finishing chapter 15. Actually, I don't know if we're going to be able to finish it today, or we'll probably defer that to Wednesday. But the idea that we introduced last time was really, let me go back into the notes from last time. Let me share the screen, and it is the OneNote. What is the OneNote? Okay, from chapter 15. So basically, last time it was this wave equation. Okay, it is really important when you're doing problems. And it doesn't matter what the field is, mechanics or electricity or anything like that. And you arrive to this equation, basically the second derivative. Again, this is a multivariable stuff. And most of the time, we're not going to be actually, not most of the time, all the time, we're not going to be solving this equation. Equals to some number positive in this case. So that's why I put it under the square in here, just to indicate that this is a positive number. And the second derivative with respect to another variable, in this case, the spatial variable. In terms of dimension, everything fits perfectly. If this, whatever the units of y, they will cancel the units of y. So y could be anything. Displacement in the case of string, water, for example, air pressure, density of the air, whatever the units of y, they will cancel on each side, basically. It doesn't matter what that is. The units of time is, of course, second. So on one side, I have 1/2 squared. On the other side, I better have 1/2 squared. I know this is a meter squared already. So this needs to cancel the meter squared and introduce the second squared. So v squared now must have the same units as those of a meter squared per second squared. The reason why the meter squared, so that it cancels the meter squared in the denominator, and the 1/2 squared cancel the other side. So this v squared is indeed a velocity from a dimensional analysis. And actually, we started with this assumption in here. What is the point in here? Way back when we started introducing this left and right waves, and we had a combination x minus vt and x plus vt. So v must have the units of meter per second. It's a speed, in other words, and it's the speed with which the wave is. So we had a combination for u of x minus vt and for x plus vt. Since x is in meters and t is in second, the same thing is true here for t is in second and x is in meter. This better have meter over second to cancel the second and end up being meter plus meter. And the same case in here too, a meter per second to cancel the second and add up second. So v is a velocity, and it has a proper dimensions, proper units, and everything else. So that's basically the equation. So whenever you're dealing with a problem in physics in general, it doesn't matter which, as long as you arrive at an equation that looks like this. The second derivative of that thing, be it the pressure or anything else, is equal to the second derivative of the same concept, which is y in this case. I started with displacement, could be any combination. And then you have this spatial derivative on this side and the temporal derivative on this side, provided they are of the second order at the same time. And this is a positive number. It cannot be negative, because it doesn't make sense in this case. There are equations that have negative numbers in here, but they're not waves. Could be anything else, okay? Diffusion or whatever, heat, something, okay? So that's basically what this equation is. So from now on, what we're going to do is we're going to be working with the problems. And once we arrive to this point, we're not going to basically say any further, hey, we know what the speed of the wave is, and it's going to be a wave, okay? So let's take a special case and then get into the string. Let's take a special case, okay? Harmonic waves. A harmonic wave is a special kind of a wave. It is a wave that has a cosine or a sine. Sometimes they're called sinusoidal waves. I don't know even how to say this thing in here, okay? Harmonic is much easier. Harmonic wave, basically a sine function, okay? Or sine and cosine are the same thing. So here is an example. So y is equal to some amplitude. This is basically what's the maximum displacement times a cosine times 2 pi of x over a number minus t over a number, okay? What this lambda is, the one I introduced in here, is just the scaling factor for displacement, because x in meters, lambda must be in meters so that the argument of the cosine cannot be, cannot have dimensions. So this is dimensionless, meter over meter cancel. And t over t also cancel, because if t is in second, I need the scaling factor in here that fixes the second, so that I would cancel the second. So at this point, those are just two numbers, okay? So this is lambda is a distance. We will see exactly what that distance means. And t is a time. And the reason why I introduced them in here, because I know the function cosine does not take dimensions, it takes dimensionless numbers. So the 2 pi is just an argument in here. So this is the combination I'm looking for. This is by definition what a harmonic wave is, okay? So if I were to draw this function, it's periodic, of course, in x, periodic in t also, both of them. So if I take t equal to 0, for example, this function looks like a cosine of 2 pi x over lambda. That means I go at the origin of time when the clock was taking 0 seconds, when the clock was stopped, and snap a picture of the wave. So it looks like this, basically. It's a cosine. So at x equals to 0, this is equal to a. And then at x in such a way that 2 pi x over lambda is equal to pi over 2. Okay, if I solve this equation, I know exactly where x is. X is going to be what? Lambda over 4 from this equation, because the pi cancels the pi and lambda moves to the other side. So if lambda equals to a quarter over lambda, this function vanishes, okay? This has no displacement. That's how the picture looks like. If I move in such a way at a distance 2 pi x over lambda is equal to pi, but a cosine of pi is equal to -1. So this is actually going to be minus a. Okay. And then if I move to a distance in such a way 2 pi x over lambda is equal to 3 pi over 2, again, cosine of 270 degrees is 0.2. Okay. And you guessed it, if I move a distance in such a way 2 pi x over lambda is equal to 2 pi, meaning x is equal to lambda. If I move a whole distance of lambda, I'm back to where I started from, basically to the distance a from the displacement. And then this continues. This is not the end of it. So this is a picture that is going to go like this. And actually, if I look at the x on the other side, so this is some origin somewhere, okay, on where the wave is. So on the other side of it, so this is to the right, for example, this is to the left, it's a replica, it's an image of this one. So that's basically how this wave looked like in space. So this is a spatial representation because t, I took it to be equal to 0. So again, this is an image at t equal to 0, an arbitrary time again, that is for the origin of time. That is how the wave looked like. As a matter of fact, this function is periodic and its periodicity is exactly lambda. So this distance repeats. I mean, if I take this chunk and basically move it around, it's not going to change. As a matter of fact, I can come to this expression here and shift x to new x prime in such a way that this x is shifted by just this amount lambda n times. It doesn't matter, n is an integer, it could be positive or negative. Then if I write this expression now in terms of x prime, y prime should be equal to a times cosine, cosine of 2 pi times x plus n lambda divided by lambda. And again, n lambda divided by lambda cancels in this case, and I will have 2n pi. And this is exactly equal to a cosine of 2 pi times x over lambda plus 2n pi. Okay, after I cancel the lambdas. And this is just a repetition of the cosine. It's the same value. So this number, for example, in here is a replica of this one and shifted by 1 full lambda when n is 1. Okay, if I go move 2 n's, I'm going to move 2 n's and I find the same number in here. If I put an n negative, it's actually a copy of this number, and so on and so forth. So it's not just for the peaks in this case, which are called crests, and it's not just for the troughs, in this case, the minima, which are called troughs. This is true everywhere for the ways it repeats itself, copies itself, basically, by as long as I shift the x-axis. So in this case, x prime and y are identical. Okay, so this function is periodic, and the periodicity in this case is lambda, as I wrote it above there, and it is called the wave length. So lambda now has a meaning. So by definition, we define it as x over lambda, but now we know what lambda is. That means the wave repeats itself, an integer times number of lambda. A single lambda, we're going to find the replica. A negative lambda, if it was before, and so on and so forth. So lambda is a distance and has a meaning now. It's called the wavelength. Okay. So lambda is measured first of all in meters, and it is the wavelength. We can define it as distance between crest and crest. That's fine. But it's also true between trough and trough, and it's true between any 2 points in the wave that are similar in behavior. Meaning, since we are coming in here, we need to be coming back in here too, because there is a point in between them where the behavior is different, and it's the same height, basically. But that's not the one. We need to be in the same direction as we're coming to have a true replication, and that is actually what the wave is. This is actually a half wave only. This is lambda over 2. Okay, so that doesn't count. So we need the full wave. Okay, so we have a meaning for that lambda. It's a wavelength. Now I need to explore the idea of t. So what I do in this case, I come to an origin at x equals to 0 and plot the behavior as this point depends on time, because it's going to bob up and down in this case. It's going to basically move, albeit we are in the same point in space. Okay, x is equal to 0. As a matter of fact, we took it. T changes still. I mean, so we're taking clock now. So we're sitting like in a boat, for example, and we're going up and down. And as time passes by, we're tracking our position vertically in this case. For example, if it's a vertical displacement. So in this case, it's going to be a cosine of 2 pi times minus t over 2. The cosine function is an even function, so the fact that I have a minus in there does not alter this expression, and keep it a equals to a times cosine of 2 pi t over t, because again, cosine is an even function. Meaning, the fact that I had a minus in here does not change things. Cosine of a minus is the same thing as a cosine, because a cosine function is an even function. Had it been the sign in there, it's going to be the same thing, except things are flipped around. That's all. Okay. And what you do in this case, you just shift the origin. Okay. So let's not talk about that. That's why I chose a cosine, because it's easier to understand in this case. Okay. So again, now the x-axis is no longer space. So this is time, and this is still the y displacement. Again, as time changes, if I choose a t equal to 0, the displacement is at its peak. Okay, so this is again a, the amplitude a. And if time is such a way that 2 pi t over t is equal to pi over 2, that means t is quarter of t, big T. At that instant, we are back into the position of the origin. So again, this is basically where we are after t over 4. Now, if we wait a little later so that 2 pi t over t is equal to pi, then in this case, if I solve this equation, it's going to give me a time that is half a t. At half a t, then, we are at a minimum. We're back to negative a now, the amplitude, we're in the opposite direction, okay? And then if I wait a time in such a way, 2 pi t over t is equal to 3 pi over 4. 3 pi, I'm sorry. 3 pi over 2 or 270 degrees, the cosine of 270 degrees is exactly 0. So we're back into the equilibrium position. And then if we wait t is 2 pi t over t is equal to 2 pi, that means t is equal to full t. Then in this case, cosine of 2 pi is equal to exactly 1, because it's the same thing, cosine of 360 degrees, same thing as cosine of 0. Again, this is basically, we're back into the same height in here, and this is the time t is equal to big T, and this time, of course, is t is equal to 3t over 4, and this is the time that is t over 2, okay? So again, if the time doesn't stick in here, so we can continue follow the clock, and we are going to repeat this pattern. And if we look in the past, we will find ourselves that actually this is how the behavior was. Okay, again, it's a periodic function, but this time it's in time, okay? And the periodicity in this case is actually the t itself. So from maximum to maximum, the time is actually full t. And from minimum to another minimum, it's actually the same thing as t, okay? As a matter of fact, from vanishing in the same condition as this one, which is in the same coming down, because this one we were going up, we're rising from the low to the high, so this doesn't count. This is actually a half a period, but this one actually is the same thing as t also. So again, this is the typical behavior of a harmonic wave. This is true for cosine and the sine, and this repeats itself every t. As a matter of fact, every nt. So if we can come in here and change the clock again and do a time shift for t prime equals to t plus an integer number of t, and we'll find that t is actually the period of this wave. As a matter of fact, then t is just, it's not just any time, but it's a specific time. It tells me how basically how much this thing is repeating in time, because we're going up and down, up and down, up and down. What time does it take to go from a complete up, for example, to back where we came from? Okay, so that is the time basically. So it's a period now, it has a meaning now. So it's not just any time, but time t, first of all, the unit for it is going to be seconds, okay, as said before, and it's the period of this wave. I know you did oscillations before, and these terms are used there too, but there is an additional term in here. There is spatial behavior and temporal behavior, and the spatial behavior is characterized by the wavelength, which is measured in meters, where the temporal behavior is covered by the t, okay, which is a period in this case, okay? Another way of rewriting this expression that is typical, you will find it in problems and everywhere else. Again, I wrote it as a equals to cosine of 2 pi x over lambda minus t over t. Another one that is traveling to the right will have a plus, that's all. So traveling to the left will have a plus. So this is actually a right wave, a right harmonic wave. So let's see if it exactly fits the bill of x minus vt. Okay, we want this expression, because this doesn't look like it's x minus vt. It's x divided by something minus t divided by something. If I take lambda out of this expression and here, what I will end up with is a cosine of 2 pi over lambda, open parentheses. I'm left with just an x in here, and I'm left with a lambda over t in here times t. So this looks like x minus vt if v is equal to lambda over t. So this is the velocity of this wave. So we know exactly what the velocity of the wave is, just by basically, because it looks similar to what we were doing earlier, in that this is a function of x minus something positive, because lambda is a distance and t is a time, and that is a strictly positive number. So this is a value, this is the velocity of which this wave is traveling. As a matter of fact, the units of v are correct, because lambda is measured in meters and t is measured in seconds. So meter per second, that is indeed a velocity. And it is not any velocity, it is a velocity of this harmonic wave, okay? So we know a lot. Now, if this number happened to be positive, then in this case, it's x plus vt, and the wave is traveling to the left, that's all. So we have both waves in this situation, okay? That is basically one way of rewriting it. Another way of doing the writing in here, because of this fraction, people sometimes don't like that. So we're going to throw in the 2 pi in here everywhere, and we're going to write it a little bit differently. So it's the same thing, but we're writing it one way or the other. So y is equal to a cosine. I'm going to throw in the 2 pi over lambda times x minus 2 pi over t times t. Now, the 2 pi over lambda, I'm going to give it a symbol, and the symbol used everywhere is the letter k. And the 2 pi over t, actually, we know that from previous classes, that this is actually omega. This is the angular velocity, okay? So this is the so-called wave number, and the other one is the angular velocity. And this one is actually called the wave number. First of all, in terms of these two symbols, this is how the expression look like. Oops. This is how the expression look like. Simply y is equal to a cosine of kx minus omega t. Okay, so this is the same thing. So we took the 2 pi and divided by, and we wrote it as simple multiplication by simple numbers in this k and omega. First of all, this relationship, which is an important relationship, this has a meaning now called the dispersion law. In terms of how v and lambda and t are related to one another, okay? So in terms of that, so first of all, we saw that v is equal to lambda over t. That is, another way of writing this expression is lambda f, where f is called the frequency in this case. Why is it the frequency? Because it takes so many seconds to go up and down, for example, okay? Or from down to up to the same state. So many seconds, 5 seconds, 2 seconds, a millionth of a second, it doesn't matter. To go up and down, well, that's it. But if I wait 1 second and see how many times I go up and down, it's expressed by the number f, okay? That's all. So t is 1 oscillation time. So how long does it do 1 oscillation? Whereas f in this case is the number of oscillations per second. Okay. So if t, for example, were half a second, that means if I wait 1 second, half of it is gone once, and another half is gone second. So the actual number is going to be 2 then. F in this case will be 2. Okay. 2 oscillations per second. Because that's the key difference between them. That's all. Okay. So f in this case is a little bit in terms of easier to write this expression in terms of this one in here, lambda f. And f has really a meaning. It's called the frequency in this case because how frequent this wave is. In other words, how often does it go up and down in 1 second? Okay. So that's a measure also of the temporal behavior. So the frequency is an important concept. Okay. Angular frequency and frequency are related to one another. Omega is equal to 2 pi over t, and t, 1 over t is actually f. So this is how they are related. So angular frequency and frequency are related via 2 pi. That's all. I mean, the difference between them is multiply 2 pi by frequency. So if the problem, for example, tell you, hey, this frequency is 400 hertz and you really need omega, you have to multiply it by 2 pi. You have to multiply it by 6.28 to get the actual angular velocity, which is expressed usually in radians per second. This is in radians per second. And the units for frequency, actually, I just mentioned it, is 1 over second by definition. But again, in honor of Mr. Hertz, we use the hertz, okay? So if it's 400 hertz, that is actually the same thing as 1 over second. Just multiply that number by 2 pi and you're done, okay? So this is in terms of the things. As a matter of fact, because 2 pi is just a number, 6.28, it's just a number, nothing else, okay? As a matter of fact, the radian itself is not a unit. It's just a number. 1 radian is what? 1.57 or something like that, right? So you can calculate what 1 radian is exactly is. It's just a number, okay? So because of that, physicists use interchangeably the word frequency for both angular frequency and frequency, okay? And this is sometimes you have to be very careful in your math what you're doing, that's all. The word frequency is sometimes used interchangeably to refer to both f and omega, okay? To refer to an actual frequency that we mean by frequency, and also to the angular frequency, which are related only by this number of 2 pi, okay? The wave number is usually the wave number, okay? We don't really do much with it, except, for example, this dispersion law can be expressed now in terms of the wave number. Remember, lambda, according to this expression that I defined for k, is 2 pi over k. So this is lambda itself is 2 pi over k. And f is, by definition in here, as it's related to omega, its f is omega over 2 pi. So this is actually omega over 2 pi. In terms of these two numbers, omega and, so we can get rid of this one. In terms of the this relationship can be written as omega over k in terms of k and omega. As a matter of fact, we normally write this expression, the dispersion law, as omega equal to kv, okay? It's the same thing, okay? The velocity and all of that. So this is how many ways now? One, this is one way. This is another way. This is a third way, namely this one. That's the same thing. I just get rid of the 2 pi. And this is the fourth way of writing the same relationship that links the wave number to the angular velocity or angular frequency and the speed of the wave, okay? You write it in so many different ways, okay? But this is only true for harmonic waves. It's not true everywhere. It's not true all the time. So you have to be very careful in here with what we mean by this expression, and it's true for the case of harmonic waves, okay? So again, the dispersion law, it's the same relationship. It's only one. It's not like I'm going to write it 4 of them, okay? So it's V is equal to lambda over T, or lambda is equal to VT. That's one way of writing the dispersion law. And this is critical because we're going to be describing the Doppler effect, and we will need this stuff, okay? Okay. That's actually chapter 16, Doppler effect. Another way of writing it is lambda is equal to, I'm sorry, V is equal to lambda F, okay? That is the same relationship, and V is equal, or omega equal to KV. Okay, and of course, omega is equal to 2 pi over T, and 1 over T is equal to F. And what else do we need? We need lambda as is related to K via this relationship. So that is basically the expressions that are all expressing the same thing, and that is the dispersion law. Okay, we'll see down the road why the word dispersion in here, what does it mean? Because you could have two kinds of velocities. This is one of them. When you have a single wave, it's only you talk only about its velocity, and this is this velocity. But when you have a bunch of them, and each and every one of them is moving with its own velocity, so in this case, you call this velocity the so-called phase velocity, and you probably will see this word in the problem. So just basically to be prepared for it. So this V sometimes is referred to as phase velocity. This is when you have a bunch of waves together moving with different speeds. And then when the bunch of waves are moving together, each and every one of them is moving with its own velocity, then there is also the group velocity. This one will be a group velocity, the velocity of everybody, I mean, as combination as a big chunk of waves moving together. So this one, the waves, one of them is moving this way, the other one is moving this way, and they're traveling. One of them is faster probably than the other, and each one of them has its own phase velocity that is governed by this one, by this relationship, okay? Whereas the other one, the group velocity, has to do with some basically how this velocity is changing with k, and then you take its derivative and you find the value for that, and that's going to give you the group velocity. So for right now, I'm going to basically ignore this one until we get into the combination of more than a single wave. Then we're going to talk about group velocity. You're going to be dealing with that one in some of the homework problems. But this one is exactly as that one. And the reason why it's called dispersion is because the wave that is moving faster is going to move away from the other ones, and the wave that is moving slower is going to separate. And in this case, they disperse. Okay, so that's why it's called the dispersion law. So if you're curious about what happened in here, so it's coming from a higher concept that involves more than a single wave. So this is basically in a nutshell how waves behave in time and space. The two key concepts in this case for waves of this type are the wavelength and the period. Okay. How you express them, how they're related to the velocity is critical. You have to have this understanding. You have to have this relationship written in one form or the other, and you write it in one form or the other. Remember the other identities to transfer it from one form or the other, depending on what you're given, okay? So that's basically how the harmonic waves are. Any questions before we go into the string? Okay. Okay. There are two main classifications of the wave, which you're going to be exploring later on in the lab today. Okay. There is the so-called transverse waves, case in point, the string waves. So that's what we're going to be starting with, and that's what you're going to be doing for chapter 15, actually, mainly transverse waves. Okay. There is another kind of waves called compression waves, or and those waves they don't behave like this, the transverse waves, but they have similar properties. They have wave speeds, and they also have frequencies, also have, if they are harmonic, of course, and they have all kinds of the behavior that is similar to this one. Okay. Chapter 16 deals with sound, which is an example of compressional waves. Okay. Chapter 15 deals mainly with transverse waves, which is a case of the waves on a string. As a matter of fact, classification is far more detailed, and that's what you'll be exploring in the lab. It's more than just, I mean, the combination of these two yields more different kinds of waves. Okay. Case in point, for example, seismic waves, which are of the two types. Okay. Both of them, they have the P wave and the S wave. And if you have ever experienced an earthquake, you feel one before the other, okay? One of them travels faster than the other, but they come together, and the second one usually does more damage. So we have transverse waves, and this is an example of that. Case in point, waves on a string. So basically take a string, hold it in place from one end, and move the other end, okay? And if you move fast enough on it for the wave to go back and come back, it's going to probably, you can have it either in the position that is as if it's not moving, and the wave could have a very high amplitude, albeit it's moving very fast in this case, or it could be an open, okay, string. So take a string from one end and basically starts to make waves on it, and it's going to travel toward the other end that is open. So a string in this case can be subject to motion that is transverse to the direction of the string. So the string is this way, and the motion of up and down is perpendicular to it, hence the word transverse, because the disturbance in this case is perpendicular to the direction of propagation. The wave will travel this way. So this is the propagation. This is the direction where the wave is going. But the actual disturbance is up and down. They make a 90-degree angle, and hence the word transverse waves, okay? On a slinky, for example, you take a slinky and you open it one side, or you compress it from the other side. So you compress it from here and you let go. So the compression in this case is along the slinky, and this compression will travel along the slinky. So in this case, the direction of travel, which is this way, and also the disturbance are in the same direction. So this is called the compressional wave. Compressional wave is the disturbance and the direction of travel are the same. As a discussion, please list the difference between the two, namely transverse and compressional wave, and give examples. I already gave a couple of examples in here. The case of a Slinky, which is compressional wave, or sometimes it's called longitudinal waves because it's along the length of this one, longitudinal waves. And the other wave is transverse wave, okay, the one that we're going to be studying right now. You can go, if you don't, I mean, think about it. There are all kinds of waves. For example, the wave on the surface, is that transverse or is this compressional? The wave inside the fluid itself, is this compressional or transverse? And if you run out of ideas, just look at the lab and you find a lot of ideas there in the lab, okay? So that is part of the discussion. There is no minimum or maximum of how many you can cite in here, a list, okay? So as long as you can come up with one at least of each, you're fine. Does this make sense to you guys in terms of task of the discussion? Yes?
Yes, it does.
Okay, very good. So basically list the difference between the two, and then at least list a few examples of each, okay? Of each of the two. Those are the two basically, the wave behaviors, okay? That's what we're talking about in here. So let's take the string. So we have a disturbance in the string. The string is very long, okay? So I'm not going to study the whole string. I'm going to take part of the string. I'm going to move from the origin somewhere on this side to a position x on the string and move a distance x plus delta x on it. So let me draw a better string. This is not good, okay? Let me draw a better string in here, okay? Probably can I draw it with a thicker pen? Yeah, let's draw it with this one. Okay, so this is string, okay? This portion of the string is located at x plus delta x. So this is how the string was before the wave hit it. It was horizontal. So I took a portion delta x of the string, okay? This part of the string has moved a distance y from, actually the string was somewhere in here, okay? So it has moved a distance y. This one has moved that, so this is probably some value, has moved a distance y plus delta y. In such a way, this is the disturbance from the next neighbor. Obviously, this is not the whole string. This is just part of the string. Do you guys understand that? So this is just delta x, that ultimately delta x, I'm going to take it to 0. Okay? I'm going to take the small value of that string. The string has a mass m and has a length L. So the unit mass per unit length, I'm going to assume is this number. So this is how much mass per unit length. Obviously, I didn't take a meter of this string. I took just a delta x of it. So this mass in here for this portion only, it's the mass per unit length times the length I took. So the actual mass in here, which I'm going to write delta m, is equal to mu times delta x. So this is the actual mass of the string. I didn't take the whole string. I just took a delta x of it. Do you guys understand that? I'm not taking the whole string. I'm taking just a portion of it. Okay? Yes?
Yes.
Okay, so this string is under a tension from the rest string. Obviously, if I take just a portion of the string, nothing will happen. So this, I'm trying to do a free body diagram in this case. So this is the tension that is coming from the other side of the string, and this is the tension that is coming from this side of the string, okay? And it's the same tension in this case because the string has the same tension. Approximately the same. I know that there is a shift it's exaggerated in here. So I'm going to take the limit that this inclination is so small. As a matter of fact, I'm going to take delta x going to 0 in such a way that this inclination, this ratio of delta x over delta y, which is the tangent of this angle theta, so delta y over delta x, when I'm going to take it very small, actually, okay, because I'm going to take a small portion of it, and I'm going to assume that this ratio, of which is tan theta, is small. Okay. In other words, delta y over delta theta, which is about sine of theta, by the way, because when this is roughly about theta. Okay. You guys remember from your Taylor series class is that basically what we're saying in here is sine theta, when theta is small, and it's measured in radians, of course, is theta minus theta cubed over 3 factorial, and cosine theta is roughly equal to 1 minus theta squared over 2 factorial. And if I neglect these terms because of the higher order and expansion terms, this will be roughly theta, and this will be roughly 1, and tan theta will be roughly theta over 1, which is theta, which is roughly sine of theta. So this is the approximation we're taking in here. So we're taking small intensity disturbances. Otherwise, this ratio delta y over delta x will be big. By the way, in the limit when delta x goes to 0, this ratio just goes to the derivative. So when delta x goes to 0, this is just the derivative when delta x goes to 0, this is just the derivative of y with respect to x. Okay, but remember y now, the displacement, it depends also on time too, because it's going up and down, but it's, as you can clearly see from this picture, it's on one side, it's different than the other. It depends also on position. So this displacement y that I'm trying to find is a function of both x and t. So this is the displacement of the string. Okay. Is everybody okay so far with me? Yes? Does everybody follow the free body diagram in here? I know you guys are making comments and I can see comments.
Yeah, it's going good.
Okay, good. Okay, very good. So let's continue that. Okay, the inclination in here, theta is measured, this measurement that I made in here earlier. Let me pick up a different color at least in here. So I have theta on this side, which is theta evaluated at x, and I have actually another theta in here that is evaluated at x plus delta x. So this is a different inclination of the string around the other side, okay? So this is basically, which is roughly tangent of theta, which is roughly dy over dx, okay? Evaluated at this point x, and the other one evaluated at x plus delta x. When delta x is thrown to 0, these two values will become very close from one another, okay? So basically, that's the whole point of this thing in here. Okay. In the x-axis, this portion of the tension is trying to move it upward. This portion of the string is trying to move it this way. Obviously, in terms of theta, this is the same angle theta in here, where this is very close from a line, because we're going to bring it very close from it so that the inclination actually exaggerates a lot in here, but it's actually going to be very close from a straight line. So this is going to be the same angle as that theta, and this will be the opposite to theta. So I'm dealing with a sine of theta times t. And in here, it's clearly the opposite also of theta. So it's going to be a sine of theta times t. So in the y direction, if I do f equals to ma, that's all we need. F equals to ma, but it's a small string, okay? So I have to consider its m. This is its m, actually. Because I took just, this is the entire mass I'm dealing with. So on one side, it's m equals to ma, and m is exactly mu times delta x. This is the mass times ma, times the acceleration. The acceleration of this string is moving up and down with as a function of time. And so the acceleration in this case is just derivative of y with respect to time twice, okay? But this function depends on two variables. So I'm going to write it as the derivative of y with respect to time. So if you're curious, this is the acceleration a, actually, that's all, okay? On the left-hand side, I have t times sine theta minus t times sine theta. But this theta is evaluated at this point, and the other theta is evaluated at the other point. The tension is the same. That's what keeps the string from moving left and right. If the tension is not the same, then the string will start to move one way or the other. We don't want that. So I'm going to follow the notation of the book, okay? This they call the tension F, and the tension F in here. So this is the tension. It's a good idea you take these notes, please, okay? And this is the tension F. Same tension. And the tension better be the same in magnitude, otherwise the string starts to move to the left or the right if there is an imbalance in between them. So what concerns us is the motion up and down of the string, which is a transverse wave, okay? So what we have on the other side, we have F times sine of theta, but this theta is evaluated at x plus delta x. And on the other side, we have F, which is sine of theta, and this theta is evaluated at x, okay? And it's just argued that sine of theta is very close from theta is equals from tangent theta. So I'm going to plug in tangent theta instead of sine theta because they are very close from one another in this approximation. So what we have in this case is F times tangent of theta. And this tangent of theta is evaluated at x plus delta x minus, I'm going to take this F out, sine of theta evaluated at x. This must be equal to mu delta x times the derivative of y with respect to time, okay? Tangent of theta also from this geometry is delta y over delta x, okay? And delta y over delta x in the limit when delta x is going to ultimately go to 0, which I'm going to take, is just the ratio of basically the derivative of y with respect to x, okay? So in the limit when delta x goes to 0, delta y over delta x goes to the dy over dx. So this is going to be f times dy over dx, and this derivative evaluated at x plus delta x minus dy over dx, but this the same thing in here. I'm sorry, did I leave it in here tangent? Why did I put tangent in here? It should be sine. And now we go to the tangent because the sine and the tangent are the same, okay, in this approximation. Sine and theta, because both of them are roughly equals to theta over 1. I mean, yeah, theta over 1. So this will be just that basically bending of the string, okay? This is what theta is equal to mu delta x times the partial with respect to t, which is the acceleration, mass times acceleration. So I'm going to divide by this delta x and take the limit when this whole thing goes to 0. So, and move mu also. So I'm going to divide f over mu in here times the ratio of, I have delta x in the denominator, and dy over dx evaluated at x plus delta x minus dy over dx evaluated at x. This must be equal to the second derivative of y with respect to time, okay? Just for convenience, I'm going to take this one and write it first and see what's going on on the other side. So I'm going to write the second term, dy over dt, is the ratio of the force over mu over the linear density times this limit. In the limit when delta x goes to 0, I have some function in here. This is a function still. That depends on x and t, because if y depends on x and t, its derivative with respect to x, still another function that depends on x and t, okay? And this is its value evaluated at x plus delta x. And this is the value of the same function evaluated at x. When delta x goes to 0, this is actually the derivative of this function with respect to x, because in the limit that delta x goes to 0, I'm dealing with the derivative of this function itself with respect to f, and which is itself is the derivative with respect to x. So this is the second derivative with respect to x. So what this looks like then is the second derivative of respect to time is equal to f over mu, the second derivative of y with respect to x, which is exactly the point we said before. Therefore, We don't need to solve this equation because, first of all, we didn't do partial differential equations yet. But we know what this is. So this is a wave. Therefore, it is a wave. So y itself as a function is a wave. So y as x of t is a wave. And we know what the velocity of the wave is. So it's the square root of f over mu. Because this term is a strictly positive number, and it's v squared. This is where v squared is supposed to be. If I compare this expression with what I was making earlier, an argument based on last time when we were doing the waves in general, this is identical to this expression, with the exception, instead of having a v squared in here, I have f over mu. So square root of that is v itself, okay? Square root of that is v itself. So that the velocity in this case is square root of f over mu. I mean, in terms of the dimensional analysis, we better find meter per second as the unit. The force is in newtons, which is kilogram meter per second squared. That is the unit for the tension, divided by the kilogram cancels the kilogram, and I will be left with meter squared per second squared. Do you guys hear me well? Because it's telling me there is something issue with the internet.
Yeah, you were having some internet problems, but
Yes.
you're good now.
Okay, very good. So basically meter squared per second squared, and if I take the square root of meter squared per second squared, it's going to be exactly what the doctor ordered in terms of speed. So this has the correct units, and it's the correct value for the speed. So this is the wave speed on string. So now everything else we said before applies. I could create a wave that is traveling to the right. I could create a wave traveling to the left. And now we are in business. As a matter of fact, the wave speed then is equal to this whole expression here, and we are in business. So I could, one potential solution in here is, in this case, y could be a right traveling wave with this velocity. So I could create a wave that has this characteristic 2 pi. I'm going to divide by lambda and write it at x minus square root of f over mu times t, because I know exactly what this wave would look like. So except now I can create any wavelength I want to. And if you are curious about the omega in this case, it's just going to be, so the dispersion law would apply in this case, square root of f over mu, which is the velocity in this case, is equal to, what is it, lambda f, or lambda over t, or all of the expressions that we were discussing earlier for the dispersion in general for harmonic wave. So this is a harmonic wave on a string. Okay, if it's not a cosine, it could be sine, it could be whatever you want to come up with. It's all of it still apply. In other words, I can still write this expression as I wrote it before. Y equals to a cosine of 2 pi times x over lambda minus t over t, or alternatively equals to a cosine of kx minus omega t, where k and omega and v are related to one another. Omega is equal to k square root of f over mu. Okay? kv. Okay, so that is a dispersion law. So this is true. Now, the only difference now, we know exactly what the velocity v is for this string, for this transverse wave on a string. So it's going to go up and down. What is its energy? I'm going to make a case for the energy now. I know if there is a particle sitting on a string, it's going to go up and down. How fast is going to go up and down? It's very easy in this case. The velocity, not of the wave, the velocity of the string going up and down. Velocity of the string up and down. That's what I'm looking at. Not the velocity of the wave. There are two kinds of velocities now. If you're sitting on a boat, for example, you could be rocking up and down. But that is not the velocity with which the wave is hitting the shore. So you have to make that distinction in here. So this velocity is clearly dy over dt. Okay? So this is, I'm going to make a distinction between, I write vy in this case, just to make that distinction here. From this expression is going to be clearly equal to the derivative with respect to t. So you're going to put a minus omega in here. and the cosine becomes a minus sign, and the minus becomes a minus times a minus, so it's going to be a positive. A omega sine of kx minus omega t. Does this derivative make sense to you guys? Yes?
Yeah, it does.
Yeah, all you do is just take the derivative with respect to t. X is constant then when you take the derivative with respect to time. And you're going to pull a minus omega first. And then you have the derivative of the cosine, which is a minus sign. So that's why you don't see in here. You see a positive in here. It doesn't matter. Even if it's negative, we're not going to be concerned with it. If I want to find the kinetic energy of this element of the string that is going up and down. So kinetic energy of this string, this element of the string, not the whole string, okay? The string could be infinite, and the energy would be infinite, okay? So we're just talking about that element, delta x, that is going up and down. So now we know its mass, which is a mu delta x, okay? We know its speed now, which is this one. So it's going to be, this is just an element of the energy. So I'm going to write it as delta ke, where delta refers to this element only, element. I'm not talking about everybody in here. I'm not talking the whole thing. I'm just talking about that element in here. Times the velocity squared in this case, Vy squared. So all you do in this case is square this quantity and you're in business. So it's going to be 1/2 of mu delta x times a squared, omega squared, and a sine squared of kx minus omega t. That is basically what the point in here. That's why if I took a sign earlier and I would be putting a minus in here, it doesn't hurt in here to have a minus still, because you're going to square this quantity. When you come to energy, you're not going to really be penalized in this case, okay? You're going to have the same quantity. If I average this sine squared, okay? And we're going to come to this expression later on down the road. So we're going to look at it this way. So this is how the sine function itself behaves. Let me just take a sine of x, okay? So this is how the sine function look like. The sine function is 0 at x equal to x equals 0 or y equal to, or t equal to 0. Doesn't matter which one you start with. So this is could be temporal behavior or a. So this is a full cycle. If you want to, you could extrapolate in here. So this is what the sine function look like. What the sine squared function would look like is, this is positive. Remember, this number is less than 1, so it's going to be steeper probably, or some behavior like this one. But then at this point, it's going to be negative. But when you square it, it's going to still be positive. And when you square this quantity, it's still going to be positive, because it's positive. The square of a negative number is still positive, and the square of a positive number. So this energy is always positive. Okay. So in terms of the energy, yes, the behavior is up and down, but the energy is always positive, because there is kinetic energy, whether you're moving in the negative direction or the positive direction, there is still energy, because the energy is proportional to the square of the speed. So that's why it's always positive. So what I'm interested in is actually the average speed. So if I'm looking just at the average speed, it's somewhere in between, these two values, okay? This is at most is equal to 1, and at least is equal to 0. So it's somewhere which is half. As a matter of fact, it's exactly half if I define the average as follows. If I define the average to be, basically take a whole cycle, from here to here, if you like, 1 over t, and sum from 0 to t of the function in dt, okay? That would be my average. The average is sum everything in this span, which is this area, basically, and divide by the entire area, because you want to find the average. So this is my average. So in this definition, if I plug in the sine squared, I'm just looking at the sine squared, okay? In here, I'm doing a temporal average. I could do spatial average in the same fashion. We'll find the same answer. So temporal average, we could just take x equal to 0 for all we care. So it's going to be sine of negative omega t, which is minus sine, but when you square it, it's going to stay sine then nonetheless. So this will be a sine squared of omega t, okay? I'm not bothering because when you square it, it's going to be the same thing. Now, there is an identity when you, I'm sorry?
Is this like average kinetic energy?
Yes, I'm trying to find the average any kinetic energy, and my point in here is that this temporal value is going to be 1/2, okay? I want to get rid of it. Let me explain why that needs to be exactly 1/2, that's all. So if you guys remember from your identities in your trig identities, cos of 2 omega t is actually 1 minus 2 sine squared of omega t. This is a trig identity, okay? Where omega t is any angle, any value. It could be alpha, okay? Sine of 2a is equal to 1 minus 2 sine of a, okay? Because it's cos minus sin, so cos of the same thing, cos squared minus sin squared. I can write it in terms of this expression in here. So this is a trig identity. And from here, we're going to make the sine squared to the other side and move the cosine to the other side so that the sine squared of omega t is equal to 1 minus cosine of 2 omega t divided by t. Divided by 2, I'm sorry. Divided by 2. Now, the average of 1/2, which is going to be integrated from 0 to t, is going to go 1/2 of t and cancels the t. It's going to be 1/2. So 1/2 is coming from this one. When you integrate dt times 1/2, it's going to be big T minus 0 times 1/2 divided by big T, and that cancels regardless of what the period is. And the other time, the cosine of omega t, 2 omega t is actually periodic function. At sometimes it's positive and sometimes it's negative, and it's going to cancel out. As a matter of fact, the integral of a cosine of minus cosine of 2 omega t or cosine of omega t is actually sine of 2 omega t divided by 2 omega, if you like. And this value is the same between 0 and t, because for 0, it's 0, and for big T, you're looking at 2 times omega times big T, and omega times T is actually 2 pi. So this is a sine of 4 pi, and a sine of 4 pi is also 0. So you have 0 minus 0. So you argue with how the function behaves, or actually plug in the numbers, and you're going to find 0. So the only thing that is left is 1/2. So the average kinetic energy, average kinetic energy for this element is going to be 1/4, because this will have another half of mu delta x times a squared omega squared. That is the point that I wanted to get at. Okay. This is the kinetic energy. The potential energy has to do with the string, because remember, when the string is completely stretched, it's going to behave like a spring, actually, as a matter of fact, where the potential energy and the kinetic energy, they exchange. So if you make that argument, the contribution from the potential energy will be exactly equal to this amount, okay? So the total energy now on the string, total energy on the string, energy on the string, energy on this element of the string, of this element delta x, is going to be E. Again, I'm going to write it as delta E, which is just twice the kinetic energy. The reason why I'm arguing it twice is exactly similar to the string in here. I mean, there is a derivation, but it's kind of lengthy. I really don't think that we should go through it. We just use the similarity between the potential and the kinetic in this case, and we are in business. So in this case, 2 times 1/4 is going to be exactly back to 1/2. 1/2 times mu delta x, that's the mass, times the omega squared times a squared. If I want to find how much energy per unit length, the energy density in this case, energy density, which is delta E over delta x, is going to be just 1/2 of mu omega squared a squared. So the point in here, this is in joule per meter, not in joule, okay? This is energy density or linear energy, because we are linear energy. The point being in here is, if you have a string that is an infinitely long string and you create disturbance in it, it's going to have an infinite amount of energy. But if you have a finite one, or if you're interested in 1 meter of it, this is how much energy it's stored in it during to this wave. It is not physics, it's not engineering until you talk about the energy, and this is the energy account of it. What is important from this discussion is that this energy is proportional, of course, to the mass of the string, in this case, linear mass, and it's proportional to the square of the angular velocity and this amplitude squared. So the amplitude plays a role too in this case, okay? So that is what is important here. The power, on the other hand, the power is delta E over delta T. So if I go back to the original expression and express it in terms of power, I'm going to have 1/2 of mu times delta x over delta t, and that is exactly actually v. So it's going to be 1/2 of mu v times a squared omega squared. Without the v, this expression is actually the linear energy. So what the power in this case is, power p, is that amount of energy, how it's traveling. So this energy is actually, this expression tells me that the energy for this wave travels from one end to the other at this rate. So the velocity is of the wave is the one that is carrying the energy from one end to the other. So that is basically an interpretation for this expression. The faster the wave, the higher the power, because it's delivering the same amount of energy at a higher rate. So this is basically how the power is. So this is in watts actually. Whereas this other expression is in joule per meter. It's an energy density, okay? Both of them depend on the square of the angular velocity, and both of them depend also on a squared, which is the square of the amplitude, which is a key element in the whole thing, the square of the amplitude. So how high you're going to make the string go up and down is critical in terms of the energy, okay? So it's very important when you're doing this experiment. So I think we explored transverse waves, at least for the case of the string, in full length. There is only one thing that is left, and that is the standing waves, okay? By the way, in this chapter, I don't know that we're probably not going to finish it today. I have looked at problem 66, problem 73, which is data problem, and you know how much I like those, and they're part of the stuff that will prepare us for the exam. And I looked at problem 77. Problem 77 is kind of not really hard to do, but at least similar in a sense to a problem that we did from chapter 2. So those are so far the problems that we're going to be exploring. But before I do that, there's still another key concept in this chapter that we need to explore, and that is standing waves, okay? So I'm going to take a string that is fixed from one end. So the string that is fixed from this end, and it's moving fast, that I'm going to assume that is fixed from the other end too, okay? And it creates a disturbance in here, and that disturbance will go and hit the other end and reflect back, okay? When it reflects back, it's going to come back, of course, with the same wave, except it's traveling in the opposite direction. So if this was an x minus vt, the other one that is coming back, so if this is going this one, the other one will be an x plus vt. That's the only difference between them. So basically what I'm going to say in this case, I have two waves, and at given points in here on the string, y is equal to a cosine of kx minus omega t. And this is the one that I meant with it traveling to the right, to the left, and the other one traveling to the right has the same dependency, except it's a cosine plus omega t. So this is the disturbance when the two meet, okay? When the reflected, so this is the reflected, and this is the incoming, okay? At a given point on the string. So they combine into this wave, okay? I argued earlier about the principle of superposition, that the wave equation is actually linear, and two waves, when they meet, is actually another wave, and this is indeed another wave. So we're going to use trig stuff to find the sum in here and see what it looks like. So again, so basically y is simply equal to a times the cosine of kx minus omega t plus kx minus omega t. I think I used the wrong sign because when it comes back, it's going to come back with a negative sign. Okay, when it flips in here, this needs to have the difference amplitude. So this is not the sum, but rather it's this difference. Okay. So in here, it's actually also the same thing. So that's the difference between them. Because during reflection, the wave actually changes from going up to coming down. Okay, if the other end was open, then you're going to do the sum. It doesn't matter. We're going to find the either way, you're going to find standing waves. Okay. So this is because of the reflected wave will have a flipped basically amplitude. So if the other one is coming with an A, the other one will come with a negative A. So the sum in this case is actually the difference between the two algebraic quantities. So cos in this case is easy to find. So cos of the difference is cos kx cos omega t. This is trig identity plus sine kx sine omega t. So this whole thing is just this term minus the second term now. This is a plus, I'm sorry. Why did I make it a minus? This is coming back in the opposite direction. So this better has a minus in it, okay? Otherwise, if both of them have the same sign, this is going to be 0. So again, in this case, we will have cos kx, cos omega t. And since I have a plus in here, the trig identity tells me that I should make a minus in here, sine kx, sine omega t. Once you're dealing with waves, you really have to remember all of those trig identities or look them up, okay? This term and this term cancel because they are the same. So what I am left with is sine of kx, sine omega t, and minus sine of kx, sine omega t, which is twice that many, and that's the end of it. So when they combine at any given point, y is still a wave, and its amplitude in this case is 2a times sine of kx, sine of omega t. Okay, this is basically when two waves meet, one of them is out of phase with the other one because it's flipped, and when they meet, in this case, they become this behavior. Okay, I just argued that the ends are fixed, so I'm going to take the string of length L, string of length L. Okay. And I know at x equals to 0, y is equal to 0 from this behavior. It's clearly a sine of kx is equal to 0 for x equal to 0, no matter what time it is, regardless of what t is, because this sign is 0. Okay, that is the setting of the problem. That's how I set up the problem. Okay, when I set it up so that this behavior actually is fixed, so I need to expect that. Now I need to fix the other side too, where it's fixed too. So that means sine of, when x is equal to L, that means y is also 0. So at any time, regardless of the time. So 2 is not 0, a is not 0. That's the amplitude of the wave. Sine of omega t changes with time. It can go up and down. So that cannot be 0. So the only place that can be 0 is sine of KL. Sine of KL must be equal to 0. Okay, which means K times L is either 0, but L is a fixed number, so it cannot be 0. But it could be pi, or it could be 2 pi, or it could be 3 pi, and so on and so forth. K is positive, by the way, always, and L is positive. So it cannot have a negative number. So K times L must be integer multiples of pi. Okay. And K, if you guys remember, is 2 pi over lambda times, this is what K is, of course, times L must be equal to n pi. What this relationship is, the pi and the pi cancel. And at the end, I will have this relationship between lambda and L, namely that L is, or I'm sorry, let me express it in terms of lambda. Lambda, if I move lambda to the other side and n down there, so lambda is equal to 2L over n. So that is the condition for me to fix the two ends of the string. And that is to choose a wavelength That is in relationship to how long the string is. The lowest one is n equals to 1. Okay? N equals to 1. And then it can have n equals to 2 and so forth. Let's see how n looks like for n equals to 1. For n equals to 1, lambda is equal to 2L, as you can clearly see. For n equals to 1, lambda is equal to 2L. In other words, here is the two ends of the string. These are fixed, okay? And this is how the wave would look like, because the wavelength is actually extends beyond the string to the other side, but this is how the actual string only. Its wavelength is twice the length of the string. So this is L, and lambda itself goes beyond. So this is the actual string, okay? And the string will go up and down, of course. So these two ends are fixed no matter what, but the other sides, they go up and down and they form this shape, okay? So the string will go up and down. This is a node, doesn't move up and down. This is a node, it doesn't move up and down. So this is fixed actually, and this is fixed. And this side will go up and down. Where the middle is, where the place is, in this case is called an antinode. How many antinodes do I have for the case of n equals to 1? Exactly 1. And how many nodes do I have? I have an exactly n plus 1, which is 2, okay, in this case. So for this case, lambda is equal to twice L. So in other words, between them is half a wavelength. So this is exactly this distance is lambda over 2. Because there is another lambda over 2 that extends beyond the string, but we cannot draw it because that's limited in this case to this shape. So let's take the case when n is equal to 2. If I go back to my original expression, in this case, lambda is equal to 2L over 2, which means lambda is equal to L. Now, this looks different. So I have to draw a whole wave between the two ends. So again, these are the two ends of the string still. And this is the middle somewhere. So I'm going to go in here and I draw a full wavelength. Okay. And now it looks like this is how the behavior is now of this string. So again, these two ends are fixed. I have this whole distance exactly, which is L, and it's equal to lambda. Both of them are the same value for n equals to 2. Okay. And this, again, is a node now. I have 3 nodes. This is not a physical limitation. This is just the wave itself cancels in that point. This is a physical limitation. So this is still a node. This is another node that appeared by itself in here. And this is the node that we fixed from the constraints of the problem. Now, the antinodes, I have 1. And I have another one in here, too. For n equals to 2, we have exactly 2 antinodes. And a 2 plus 1 nodes. So this seems to be a pattern now that is developing. Let's look at n equals to 3. N equals to 3. If I look at the expression in here, it's 2 lambda over 3. Okay, 2 lambda over 3. So I have to be careful in here how to draw this shape in here. So again, these are the 2 physical sides of the string in here. Okay. I have to divide this side to about 3 portions, equal portions. So this is 1 and this is 2, okay? So this is portion 1, 2, and 3. So in this case, the wavelength is lambda is 2/3 of an L. So this is a full wavelength, okay? And I have a half wavelength sticking by itself in here. So this is how the shape of the string would look like. It's going up and down, and between them, this is a node, this is another node, and the 2 external nodes that are constrained by the problem itself. Okay, how many antinodes? We have this one antinode, this one is an antinode, and this one too is an antinode. For this case, again, lambda is equal to 2/3 of an L. There is actually half lambda going to the other side, which we cannot draw. So lambda is equal to 2 over 3L, okay?
Hey, Professor.
2/3, I'm sorry?
I'm starting to see a pattern here. Is n also equal to the number of antinodes?
It's always like that. Yes, that's the point that you're coming up with. Thank you very much. Okay, that is exactly the point that I'm trying to draw in here, that the number n in this case is actually the number of antinodes. And if you're asking how many nodes in this case, it's n plus 1. So in this case, there should be 4 antinodes. I mean, 4 nodes and 3 antinodes. Okay, that's a very good point. So in this case, so if somebody asks you, for example, for n equals to 17, you know what you're doing. For n equals to 17, lambda is going to be 2 over 17 L. I'm sorry, 2 over 17 of them. So you're going to take the length L and divide it into 17 portions, okay? And those 17 basically portions where you're going to draw the portions in it will have exactly 17 antinodes and 18 nodes, okay? And that's basically the shape that we're coming up with in here for standing waves. And this is now, because they combine, there will always be this behavior. They will always be given by this expression, okay? So n in this case will all satisfy this equation, will all satisfy the so-called, these are so-called boundary conditions. Boundary conditions. The constraints on the string in here, okay? So this is how the constraints of the string is. So this is basically how the standing waves are. This is a beautiful lab. When we were in session and we do it and we compete, and you know, it's exciting. And I know some of my students, they start taking pictures with their cell phones for anything when they reach n equals to 8 and n equals to 7. It's very hard to do, I mean, to reach those, because especially when, I mean, one of the problems, I believe problem 73 is the one that I chose, mimics that experiment actually. It's similar to it, so hopefully you guys will appreciate it. That's actually on standing waves, okay? And if you ever heard of string theory, it actually deals with some sort of standing waves. That's the superstring theory that is the most modern theory. We still have about 3 minutes, and I know the next ideas are big ideas. I think this is the main ideas in terms of a lecture. On Wednesday, when we meet back, we're gonna devote it mainly to problems. We have really the ideas of the lecture, basically all of it touched upon, okay? And the dispersion law, which is a key concept in here, the standing waves, which are important in here, and they rely on the idea of harmonics, okay? Both of them, harmonic waves, okay? Namely the sine and the cosine. And there is another representation. I use trig in this case, okay? There is several representation of waves, okay? And I want you to be aware of them at this point, just to be aware of them. The one that we are going to hit on in optics when we get into optics is which is actually waves too and things like that, is probably going to be what is the word now? It escaped my head. It's phasors method, okay? So we're going to probably use the phasors method. The other method that is used to adding waves also is complex numbers. Are you guys familiar with complex numbers a little? Yes, no, maybe. You had them in math somewhere? Okay, good.
I would like a little more practice with them.
Yeah. So I know some of you are sitting in my other class also, the 4B. And at some point, probably we're going to be using complex numbers, okay? Because they make the problems that are extremely hard at times look a lot easier than what they are, okay? That's the promise of complex numbers. You take a very hard problem and use complex numbers and make that hard problem easier, okay? That's the idea of it. Short than that, you can use phasors method, which is a graphical method. That too, we're probably going to talk about it. But for right now, we use trig because both methods, the other two methods, they work only for linear waves, for linear equations. When you're dealing with nonlinear waves, which is really nonlinear behavior in general, which is typical in real life, you can't use those methods. You have to come back or use them in approximation if you wish. You have to come back to what we did today, namely trig, okay? Which is the hard way and the dirty way of doing things, but that's basically at the end what saves the day, okay? So I know it's 10:25. We'll just hit the mark exactly when we're supposed to leave. Hopefully I see you guys in the lab later on, because it's a very important lab that I want you to actually explore something that we missed on the first lab, and namely the grading and how that works. And it explores a lot of these ideas also in detail. Any questions before I stop the recording? No? I'll see you later. Okay, we will discuss also the homework at some point in either this afternoon, most likely on Wednesday too, on how that is going. See you guys.
Take care, Professor.
Bye. Thank you.